Hello, welcome to your lesson on logarithmic growth versus exponential growth. So you're very familiar with exponential growth already, which looks like this. Logarithmic growth looks like this. Right, this is a very big idea. Logarithmic functions are an important way of modeling many real-life scenarios. Let's take some notes on the page that has been provided to you. First, let's begin here. We have an exponential function, and we're going to fill the table of values. So what I want you to do is put a -2 in for the x here, and think about that. You have 2 to the power -2, and what value does that give you? Hopefully you got 1/4, because 2 to the -2 means you can put it 1 over 2 to the +2, which is 1/4. You gotta remember how your indices work. All right, try that with -1 now. Put -1 in here. Let's see what you get. 1/2. All right, let's put a 0 in here. Actually, let's go all the way down the line here and see if you can get all those values. Some will be trickier than others. Okay, when you put 0 in there, anything to the 0 power is 1. When you put 0.5 in here, well, 0.5 is 1/2. So to the 1/2, remember when you have a half as your exponent, that means the same thing as the root or square root. So square root of 2 is actually 1.41. You put 1 in there, well, obviously 2 to the first power is 2. If you put 1.5 up there, it's like saying 1.5 is the same as 3 over 2. So that's like saying 2 to the third power and then taking the square root. So it's like 2 to the third power and the square root of that, which is 2.8. And then 2 squared, of course, is 4. Let's do the same thing with a logarithmic function of base 2. So first number we're going to put in there is 0. 0 goes in here. And don't forget logs, right? When you change them to exponential form, this one would change into 2 to the y equals x. So in other words, if you put 0 in for x, you're thinking 2 to some power equals 0, right? 2 to some power or some exponent equals 0. So how can you get 2 to some power be 0? Well, that does not exist. It is impossible to have 2 raised to some exponent and get 0. It's impossible to get an exponent. That makes 0. Let's put 2 to, let's see, put 0.5 in here now. What happens when you put 0.5 in there? Hopefully you got -1, because 0.5 in here would mean 2 to some power gives you 0.5 or 1/2. So 2 to some power is 1/2. Well, to get 1/2, it would have to be 2 to the -1, because that would make the 2 go into the denominator and you have 1 over 2. All right. Now, let's continue on. See if you can fill in the rest here. You may need your calculator for some of them, but the ones that you don't need to, please do just in your head. Next one's 0, because if we put 1 in here, we're saying 2 to some power is 1, and 2 to 0 power is 1. Then we have 1.5. That one is 0.58. Then we have 2. If 2 goes in here, we have 2 to the first power. So 1 is 2. Then when we have 4 in here, 2 to some power is 4. Well, it's 2 squared. And 6, you may need your calculator. That's 2.6. Now that we have that, please plot both of them together on the same coordinate plane. So plot the exponential one, plot the log one, and see what the two curves look like. And do you notice anything? Well, here's the graphs. Here's the exponential. Here's the logarithmic function. Hopefully you notice they are inverses of one another. All right, inverses was a topic of our recent lessons, and it is really, really important. The main reason we did inverses is to notice that exponential growth and logarithmic functions or logarithmic growth, those are actually inverses of one another across the line y equals x, right? So that's y equals 2 to the x power. This is log base 2 of x. And remember, there's an important point on most exponential right there, 0, 1. And notice, since log is the inverse, it has a point that it passes through also, which is 1, 0. So those 2 points are considered like these key points that allow you to graph these properly or move them around if you're translating them. So remember that log functions always pass through this, but not always. If they're translated, they don't. But in general, they pass through there. They get close to the axis, go through there, and then they start to plateau here. All right, exponentials and logarithms are inverses of one another. This is a key point. Please keep it in mind. So in general, log functions look like this. Again, they'll pass through 1, 0. And there is something called an asymptote right here. Just like an exponential, if I go back to there, exponential functions have an asymptote right here, right? They never get to that. Log functions has an asymptote here because they're inverses of one another. So this asymptote, when it be reflected over this line, becomes this asymptote for the log function. So there's the asymptote. It's at x equals 0, vertical asymptote. All right, now think about these two questions and answer them. Why is 1, 0 a point on y equals log x? Why is that point on this function? And why can x values not be less than 0? In other words, why does this log function not go behind here and go into the negative area? All right, hopefully you kind of thought through the answers there. 1, 0 is a point on a log function because 1, 0 means you put 1 in here. And the only way to get 1 for log base 10, this is log base 10, 10 to the 0 power equals 1. That's the only way to get this to work. All right, and this question 2, why can x values not be less than 0? Because when x is less than 0 here, then you're thinking 10 to some power makes a negative number, and that's impossible. Anything raised to an exponent is going to be a positive number. Think about that. Even if the exponent is a negative number, it still just creates a tiny value, but not a negative value. For example, an exponent of negative 5 would create 1 over something to the 5th power. All right, so now that we've seen that logs and exponentials are inverses of one another, so fill an inverse there, we're going to find the inverse of each of these functions. Here's one that's non-log, it's just a linear function, but using what you know about how to find inverse functions, do that for this. Remember, you begin by switching the x and y values to create the inverse. So the inverse there should be this. You've switched the x and y, but now we rearrange things, so we solve for y. So moving that 5 over there, and then dividing by 3. You could have written this one fraction with 3 here. All right, so that's the inverse of this one. Now do the same for these. Now that we know logs and exponentials are inverses of one another, let's try here. What would the inverse of this be? Begin by switching the x and y. All right, so I've switched the x and y values, so x equals 2 to the y. Now if I'm solving this for y, well, we can use the definition of a log, right? To solve for y, we can rearrange this from exponential form, change it to log form. In log form, this would be log base 2 of x, and there is the y. So notice that this exponential has turned into this log function. That should make sense. Those are the two we just graphed above, and we found out that they're inverses from each other. So the inverse of this must be this. Now let's try the reverse of that. So here's log base 2. And if we find the inverse of that, well, hopefully it ends up being this because these two are inverses of each other. So let's begin with this. Switch the x and y. So this is now x, this is y. Now change this to exponential form so that we can solve for y. So it'll be 2 to the x power equals y. So there it is. So this one changed into that, and that one changed into this. And that makes sense. They are inverses of one another. All right, let's try some more. Finding more inverses. These get a little tougher. There's more constants there. So let's see what happens. Try this one. Find the inverse of that. Right, the inverse of that would be, first of all, switch the x and y like this. Then we can write, change this to exponential form in order to get that y out of the log, right? So we have 4 to the x here equals this, y minus 3. And we're going to add 3 on this side. There it is. And we have our inverse function, which is an exponential. So this log has an inverse, which is this exponential. And notice this one here is a translation along the x-axis, and this becomes a translation on the y-axis. It's like the inverse operation happening. All right, try to find the inverse of this exponential. Well, the inverse first step is to exchange the x and y. This is x, this is y. Now to bring that y down, we'll change this to to log form. But before that, we should move this 2 over to that side. So we have x minus 2. There's 5 to the y. Now let's change it to log form. Now that this exponent expression here is isolated, we can do that. So log base 5 of this equals y. So there we have our inverse function. This was exponential, this is log. Again, notice this is a horizontal translation, and here we have a, vertical, and this is a horizontal translation. Last one, try to find the inverse of this. To do that, switch the x and y. I've done that here. Now this is log base e, so I'm going to take this log form, change it to exponential form. It will be e to the x power equals this, and then move that 7 over there to solve for y. So there's our function. Began as a log or natural log, log base e, and the inverse is an exponential form with a base e. And again, minus 7 plus 7 here. Makes sense. All right, 3 more. Find the inverse of each of these. First one, rewrite it in like this. Instead of function notation, use y, then switch the x and y to make the inverse. Then divide by 3 here to isolate the log statement. So divide by 3. And then you can change the exponential form, 5 to this power equals y. So that means our inverse is this, exponential. Try this one. All right, for this one, again, rewrite f of x as y. To do the inverse, we switch the x and y values. Then we do log with this base of x equals the exponent 2y. Now there's a 2y here. I'm going to rewrite this as ln, natural log. Then there's a 2 here, so divide by 2. It's been divided by 2 to solve for y. Therefore, the inverse function is natural log of x over 2. And last one here. All right, here we have the function. Here's the inverse. The x and y have been switched. This can be written as log base 2 of x equals y minus 3. That 3 has then added to this side to get this. And that is now our inverse function. Began as exponential, now it is an inverse, same base, 2 and 2. All right, this one also I'm going to show a graph just to confirm that they're inverses. Here's the graph of log base 2 of x plus 3. Here's the graph of 2 to the power x minus 3. Notice they are perfect reflections across y equals x, therefore we can confirm they are inverses of one another. All right, last thing on your page there, we have this log function, and we have this one, which is a translated or transformed version, right? We see a minus 2 here, plus 4 here. How has it moved? How has this one changed because of the transformation here? What has happened? Well, we've noticed there's a minus 2, so it's a plus 2 horizontal translation, and here's plus 4, so we go up 4 vertical translation. So now here's what they look like. The original is here in red. It passes through 1, 0. That 3 affects it in some way. The base changes kind of the shape of it. But now this one has moved 2 right and 4 up. So take the main key point. Here's the original asymptote, by the way. Take the key point, go right 2, up 4. There's the key point, which has been moved from there to there. The asymptote is always 1 away from there. So the new asymptote is 1 away. It's here. And that asymptote then is at x equals 2. All right, it asks for the asymptote of the transformed one. Here's the new graph. And what is the domain of the transformed one? Well, the domain, what x values? It doesn't pass this asymptote here. So the domain is x values greater than 2. And the range, well, this goes forever up and forever down, close to the asymptote. So the range is all real numbers. All right, please practice some more. There's some problems for you to try. Not too much, but a few just to practice this skill linked on the lesson. You can do it.